Now let us study the results of first law. From first law, this law enables us to define force and inertia. From first law, we define force and inertia. If no external force acts on an object, its acceleration is 0. If no external force acts on an object, its acceleration is 0. This is obtained from the first law because the velocity remains constant. When the velocity is constant, the acceleration is 0. So this is the result of the statement of first law. Now let us come to the force and inertia. First law defines force. Force is a physical quantity that changes or tries to change the state of a body. Force is a physical quantity that changes or tries to change the state of a body. Inertia. It is the property of the body that retains or tries to retain the state of a body. Mass is a measure of inertia. Inertia is that property of the body which tries to retain the state of the body or retains the state of the body, and it is measured with mass. Inertia is measured with mass. Examples of inertia. Examples of inertia. A standing person in a bus that starts suddenly falls backwards. A person falls backwards if the bus is taken off suddenly. This is because his feet move forwards. His feet move forwards while the entire body will remain in the state of rest. This is an example for inertia of rest. The inertia of the body is initially at rest, but when the feet are dragged by the movement of the bus, the body inertia remains to be at rest, hence we falls backwards. This is the example for inertia of rest. A standing person in a moving bus falls forwards if it stops suddenly. If a moving bus stops suddenly, a person standing in the bus falls forwards. This is because his feet are brought to rest while the entire body will remain in the state of motion. Before brakes are applied, the bus and the person are in the state of motion. So the inertia of the man is in the direction of motion. It is in motion. Hence, when the bus is stopped, the feet come to rest, but the body will be moving in the direction of motion. Hence, the inertia moves forwards. So we feel as though falling forwards. This is an example for inertia of motion. Momentum. Before we study second law, we have to understand momentum. We know that momentum is the product of mass and velocity. P is the symbol used for momentum. M is mass, V is velocity. mv is momentum. It is a vector quantity. It is represented by the vector P. The direction of momentum is same as that of velocity. The velocity is from left to right, so the momentum is also from left to right. If a particle is having more than one momenta, say if the particle is having two momenta, P1 and P2, since momentum is a vector quantity, the total momentum, the resultant momentum will be the vector sum of the momenta P1 and P2. We know that if there are two vectors PQ at an angle theta, their resultant R is given by square root of P square plus Q square plus 2PQ cos theta. And the direction of this resultant with P is given by alpha, where tan alpha is equal to Q sin theta divided by P plus Q cos theta. With this relation, we determine the direction of the resultant. So we can apply these two relations to find the resultant of the moment of P1 and P2. From the second law, F is proportional to dP by dt, but by definition of the unit, we make the proportionality constant as 1. Hence, force is equal to dP by dt. we can make the relation F equal to dp by dt by choosing a unit of force such that the proportionality constant becomes 1. Hence, we can use the relation F is equal to dp by dt. In the statement of second law, we notice that the change in momentum is in the direction of force. To understand this, see the first figures. Pi is initial momentum, Pf is final momentum, dp is the increase in momentum. See the magnitudes of the vectors Pi and Pf. Pf is longer than Pi. The difference will be equal to dp. Here, in this case, the force is applied from left to right. Since dp is from left to right, the force is applied from left to right. So, dp and F are in the same direction. So, dp will be in the direction of force F. If Pi is horizontal and force is applied vertically in the upward direction in the second figure, then dp will be in the upward direction. So, the resultant force Pf will be the vector sum of Pi and dp. It is shown in the third figure, right side. Then the magnitude of Pf will be square root of Pi square plus dp square. Like this, we have to find the resultant or final momentum by vectorially adding the initial momentum and the change in momentum. So, we have to understand that the dp, change in momentum, will be in the direction of force. Relations for force. From second law, F is proportional to dp by dt. The constant of proportionality, if taken as k, then F is equal to k dp by dt. dp by dt is equal to ma, hence F is equal to kma. The value of k is made equal to 1 by proper choice of units. Suppose if you take SI system. In the SI system, the unit of force is Newton. So, F is equal to 1 when m is equal to 1 and a is equal to 1. Like this, we define Newton. That is, Newton is that force which produces 1 meter per second square acceleration in a mass of 1 kg. By using this definition, we make k is equal to 1. Then the relation becomes F is equal to ma or F is equal to dp by dt. F is equal to dp by dt. But P is momentum mv. From mathematics, we obtain the relation as F is equal to d by dt of mv. F is equal to d by dt of mv. Here, m and v, there are two terms, mass and velocity. And any one can be changing. If velocity is constant and mass is changing from vector algebra, from calculus, we will get F is equal to dm by dt into v if v is constant. In mathematics, we write this relation as F is equal to dm by dt into v. If mass is constant, then F is written as dv by dt into m or m into acceleration a. If mass is constant, m into dv by dt, that is equal to ma. If velocity is constant, F is equal to dm by dt into v. Like this, we write the relations for force. From Newton's third law, we will get action and reaction are equal and opposite. To understand these forces, let us consider collision of two bodies. Before collision, let us suppose a body of mass m1 is moving with the velocity u1, say 1, body number 1, and another body number 2 is having mass m2 and moving with the velocity u2 in the same direction. See, the vector over m1 is larger than the vector over m2. That means the velocity u1 is greater than u2. Then if u1 is greater than u2, then the first body collides with the second body. During collision, the forces applied are collision forces. These are known as internal forces. Now let us assume them as F12 and F21. F12 is the force applied by first body and second body. F21 is the force applied by second body and first body. Then F12 changes the momentum of M2. F21 changes the momentum of M1. F21 is opposite to the momentum of M1. F21 is opposite to the momentum of first body. Hence, the momentum of first body decreases. So, the velocity of the first body decreases. So, the final velocity is V1. Its vector must be having less magnitude than that of U1. And the second body, M2, the force is applied in the direction of velocity or momentum of the second body. F12 is in the direction of its momentum, M2U2. Hence, the momentum will increase for the second body. So, the velocity of the second body increases. So, V2 will be greater than U2. V2 will be greater than U2. V2 is the velocity of the second body after collision. V1 is the velocity of the first body after collision, and V2 is the velocity of the second body after collision. Here, the change in momentum is dp, and the direction of dp is from left to right on, it is from left to right on the second body. It is the direction of F12 because the change in momentum of the second body is caused by the force F12. Hence, dp of the second body will be from left to right. dp of the first body will be from right to left. dp will be equal to F12 into dt, where dt is the time for which the collision has occurred. If dt is the time for which the collision takes place, and the change in momentum dp will be equal to F12 into dp.